in frame. Good evening, everyone. I am Nacole Farley.
I'm Joseph Rogers.
I'm James Short.
And I'm Garrett Larson.
And we are the conductors here to present regarding our project, the interactive dual train display. Throughout this presentation, we'll review a few topics, including our problem statement at hand, our architecture overview, then we're going to dive into the hardware, the software, the user interface. We're going to do an evaluation of our performance based on budget, labor, and tasking. We're going to talk about our project deliverables overall, future work, potential applications of this project, and then we're going to have time for questions.
Alright, so the problem statement is the lead into every project, right? So every
engineering solution obviously always starts with a problem. So in this case, our problem is related to the DCE department. Over the years, the department has unfortunately experienced a pretty steady decline in enrollment due to a variety of factors, but ultimately the overall enrollment has pretty much stayed steady. So our aspirations here is to inspire, and hopefully our solution will provide a meaningful element for stabilizing the enrollment and hopefully inspiring future students and current students alike. All right, so we'll first break into the system architecture. We have 4 modules, as you see here. I'll briefly go over each module and the function that it provides. So first we start with module 1. Which is the power supply, which is essentially the heart of the project. It has 2 power supplies, an AC to DC supply and an AC to AC step-down converter. Essentially, this provides all the voltages necessary to power the H-bridges, the ancillary functions such as the oscopes, the Explorer board, the logic control center, and of course the solenoids and trains. Next, we have the second module, which is the brains of the project, the control system. So as you see here, as she was pointing out, that essentially has interactions between the photosensors, the LEDs, and the position and PWM, which is located on the next module, the UI. And of course, the next module is the user interface. This module primarily deals with pulse width modulation, pulse modulation, which is speed input. And train priority, which of course controls which train has essentially priority to the shared section. Finally, we have module 4, which is the physical display, and that is, as it says, it's all the LEDs in the actual physical track. That's wrapping up this slide.
All right, so the hardware architecture. In order to power the entire train display, we wanted to have it single plug into the wall, and then we had to step down each of the voltages for each of the sections. So James went over all of the modules, but within the modules, we have auxiliary functions that need different voltages. So the AC to DC transformer power supply that we have steps it down from 120, 60 hertz to 24 volts plus or minus a volt. That's on 2 ports. Now we divide that 2 ports up into port A and port B. Port A is going to be for the trains. So all the power consumed by the locomotive trains going around the track is coming off of that single port. Everything else is going to be off port 2. So as you can see, we had to put quite a bit of regulators to step them down using LM chip microchips, LM317s. That works off the proportional difference of the resistors that are on the outside of the chip feeding in, and then that controls the steps down the voltage to the proper levels. Levels we needed, more specifically, were 3.3, 9 volts, and 12. All of those then were sent downstream, which I'm pretty sure everyone saw in our walk around. Everything was working.
All right, so next up, we're going to look at the software. And so with the software, our overarching goal was to create a system that would avoid collision between both of the trains. So everything that we created having to do with the controls was centered around that idea. So when it comes to the controls, basically we have a velocity control where the user can control both trains independently. A position indication circuit which allows the user to see where the trains are along the track via LEDs that are on the user interface. The track switch control circuit, which allows the user to switch between which train has the priority at the junction. So if they're about to collide, one will stop and the other will go depending on that user setting. And then we have the priority assignment circuit. Sorry, I actually mixed the two up. So the track switch control circuit is the actual physical track switching via relays and solenoids at those junctions. And then the priority assignment is what I said before, is the switch that the user controls to determine the priority. Okay, and then we can move on to the user interface and visual display. And so what that is what everybody kind of saw with all of the knobs and the switches and the track representation with the LEDs and the O-scopes and everything. So that is kind of the central unit for the user to control the entire system, control the speed and all of that, and try to make them crash. I hope a lot of you were able to try to make them crash and maybe not succeed. It would have been cool if you did though. I know one person was able to make it happen, but we won't talk about that. So anyways, yeah, the user display or the user interface and visual display consists of two potentiometers for the user to control the speed, a priority switch in the center, which allows you to switch between which train has the priority, two pulse width modulation oscilloscope displays, which are connected directly to the PWM output by the PIC 18. The track display, which is the representation of the track, the miniature representation with LEDs lined along it so you can see where the trains are. And then the LCD display, which allows you to see a velocity representation of how quick the trains are actually moving in inches per second. And so with all of these controls, we figured this kind of gives the user the maximum amount of input that we would want them to have and still allow the trains to operate without colliding.
So with the accomplishment of this project, we had a few different metrics that we wanted to evaluate performance. The first one, of course, being labor. We actually tracked everyone's hours using Microsoft Forms input and found that we were able to maintain under 12.05% below our labor budget. That was probably due to winter break, if I'm being completely honest, because we worked a lot in the second half. As for material, we were able to spend $989.20 of our $1,000 budget. However, that does also include sustainment sparing material. As for tasking, within our Microsoft project online, we actually had 53 different designated tasks for this project. Of those, we only have one outstanding, which is our final report. That, of course, is not yet due until Monday. So everything has been completed on schedule and as projected. With regards to the project and the actual deliverables of themselves, of course, we have our integrated display system, which we do have a small clip to show. We also have our sustainment sparing, as previously mentioned, with regards to extra oscilloscopes, H-bridges, LEDs, plenty of extra LEDs should anything break. And then we do have everything stored within the central repository in Microsoft SharePoint. The idea being that should anything happen to the system, even when we're gone, someone can readily access all of the data sheets, all of the 3D printing files, so that they can reference all of it and be able to utilize it for ready repairs.
And finally, we have future work. This is essentially tasks that will be completed in both the near term and the far term, at least the possibilities there. So the near term is things that we could not accomplish due to mostly location of where the train is assembled. There's going to be a plexiglass installation. We'll have to move eventually the track into the hallway to the main display where it's going to be. None of those things we can control under the conditions. And finally, there's a power wire that we have purchased, but again, we're not going to trim it until it actually gets to the final location. The possible future work is something we discussed with Dr. Hagan and a few other people. Perhaps somebody picks this project up later. You can add additional train cars, which will cause a potential coding change. Is of course, depending on the sensors are placed. If the cars were to exceed the sensor locations, i.e. getting two sensors, that would probably cause an issue. Secondly, we have a digital display. That was a stretch goal, but due to time constraints and budgetary concerns, this was something that perhaps a follow-on student group can accomplish. And finally, a very long stretch goal was the train camera. And that concludes this slide.
Does anyone have any questions? I had to have the train roll in. Thank you for appreciating that. You should have seen our shark.
When do you make it pretty?
Why didn't I?
No, when?
When? So we're actually going to be working on that within the next 2 weeks. Joe and I are also going to be pulling a lot of extra hours with our summer hobby once we're able to install it in the final location to make sure that there's full coverage and the table itself. That way everything looks like an actual landscape. And then we're also going to be working on concealing all of the wiring beneath the table.
As well as the power supply enclosure, which is
Yes.
still required cross-departmental cooperation, which has been a little bit of a delay.
Can you talk about who was your client and what was specifically asked of you by your client? What was the requirement of your client?
Yes. So to reference this, I ask that we please go back to the software section. I actually went line by line for the project form in last semester and pulled all of this from his requirement for how the operation needed to work. So these are the requirements of Dr. Hain, and of course with all of this being so integral to the software, that's why we placed it within this slide. And as previously maybe mentioned, our client is Dr. Hain for this project, and he's been incredibly helpful in providing lots of materials so we don't blow the budget, and also being able to give guidance for our coding questions. He is also on the curse.
Can you describe what was the biggest problem you faced?
So we were all organized in different aspects of the project. My portion, I learned how to use SolidWorks for the first time. I'm not a SolidWorks gal apparently, but I did my best in being able to design the user interface panel for operation. Additionally, I did the communications for the velocity display. Originally, I used MSSP/SPI communication in trying to expand and utilize different LCD panel. To do so, we found that there was actually a chip that was on the back of the board that wasn't supposed to be there. So then I tried to change lanes and go to I2C communication. I'm apparently not an I2C gal either. So I went back to SPI because I knew that was what worked. So that was my challenge of the year.
Sure, I'll lead in with that. Essentially, my primary issue was mostly had to do with logistics. We ordered some parts and they did not arrive or did not arrive quite in time as we would have liked. So that constrained us and forced us to deviate from some of our plans, such as the track and perhaps even a couple other things.
So I think the most difficult part for myself was dealing with C, which is a pretty common language for engineering projects and things, but specifically the algorithm for the anti-collision was, it took a lot of Excel sheets, spreadsheets, and logic truth tables and things to actually iron out how it would all work, how we can keep track of things in the back end, and really make the anti-collision robust enough so it can't be broken, even though it can at this stage, but it's still, an early stage. It takes time to debug everything and get it perfectly working. So I'm very happy with where it is though.
From my side, I think there was a little bit of scope creep in some of the ambiguous, not solid deliverables aesthetic-wise, and that then trickled into some of the delays we talked about earlier with components and getting things in on time, hence the way it looks now. So for me, it was, my eyes were a little bit bigger than my mouth was trying to solder every single little resistor and capacitor. I really would have liked to maybe had a semester to actually make the boards on a printed board or something to make it easier. But yeah, there was a lot of late nights for that, so that was probably the hardest part from my side.
I have a question. On I think the first 2 or 3 slides, You mentioned that you use an AC to an AC converter step down. What did you use that for?
It was used for the solenoids and relays, so that's the only function of the AC to AC. It steps down 120 to 9, 16, and 24. We only really use the 9.6. Yeah, so essentially it drives the relays, which drives the solenoids, which allow the trains to switch between each trains.
So from 60 hertz to 60 hertz? Or?
Yes, sir. Yep. Essentially this is straight step down, so 120 to 9 or 16 or 10.
Was it like a transformer or?
Yes.
So in fact, you can see it right here, and what we did is after we're going through the spec sheets and discovering what, through trial and error, because we didn't have the exact specs of the solenoids, we were able to use a standard doorbell transformer from a house.
Cost effective and gives us multiple voltage levels, because the solenoids did not have a spec sheet either. So trial and error essentially.
Thank you.
Thank you for your time.